All right. So hello everyone. We're the Midnight Sirens. We worked on the parking spot detection. We worked with computer vision this time instead. Our main project was as uh, our project states, our computer vision will take a look at an image or feed of an overhead parking lot, and it'll determine which spots are occupied and which spots aren't, so that it'll make ease of access for managing your parking lots as well as a driver looking for a parking space. Now I'll hand it over to Prisha for the first step of our process in this.
The first step of our process was collecting data and annotating data. And to find data, we could use web scraping, searching up different data sets and download them to our laptop, or use some pre-made data sets that were already in RoboFlow. When we found the data, we annotated in RoboFlow, and we had two classes, which were the occupied spaces for the occupied parking spaces and the unoccupied spaces. Initially, we had multiple mock classes uh, for obstructed parking, restricted parking, as well as parking signs. But we realized that our model was getting confused because a lot of these classes looked similar and it couldn't really tell the difference. The data that we found consisted of various pictures of parking lots from overhead and even from the ground view. And the data all had different amounts of parking spaces filled up so that the model had different instances to train itself on. And finding data meant we needed parking spaces that had enough variety between each other so that our final product would work effectively in most cases. I'll pass it on to Leo for the next step.
All right, so in the Google Colab training preset provided by our team leader, Nathan, we cloned the GitHub repo and then we imported PyTorch libraries, aka our dependencies. And using the data collected from the annotated images from RoboFlow, we then imported datasets from RoboFlow into our parking detection directory, more specifically into our YOLO v5 folder, YOLO v5 being the object detection model that we used. And from here, WAN-B is installed, WAN-B being weights and biases, which is a tool used to image the datasets into graphs and charts. And from here on, the training is thus commenced using train.py, in which our batch size and epoch sizes are labeled, respectively being 64 batches and 250 epochs. Depending on the team member, training time varied between 20 to 40 minutes, and so did the number of epochs completed. When training is completed, we then can click on the WAN-B link generated in Google Colab, which then allows us to view the training metrics. These metrics basically outline whether our AI is able to properly analyze images with the proper confidence values. And from here on, Dev will explain how we can use the model to get results.
Yeah. So the most important thing to know about like any object detection model is that it's just doing it on image. So you're really looking at pixel coordination essentially. And so this has immense applications for our project as well, where you can take any input image and just apply any sort of transformation. It could be like on an orthogonal plane or whatever, and you can still run predictions on it. So while open and occupied parking spots are interesting for self-driving car purposes, they're also applicable for different applications from video to any sort of like feed that we can think about. But in terms of actually setting up the pipeline for getting our data and then getting user input and then using our model to actually make the predictions, what we first did is actually just exported the model parameters in a .pt or like in a pickle file format. And this is a pretty common, straightforward system where you can essentially use like pre-built torch libraries or PyTorch libraries to load in these parameters into like an empty YOLO v5 model. And that allows you just to run predictions on any type of model, obviously. Next step, what we had to do is essentially create like all the file logic. So when someone uploads a file onto like a Flask app, you have to be able to like, keep it safe and secure. You have to have like local directories to like manage all the processes. Then obviously just a simple, then you just run a model that predict, and the YOLO v5 model that we've trained automatically does the recognition for its bounding boxes on any given image sample. And we get a bunch of different results off this. We get a confidence interval. And these values are basically just like percentages to talk about, whether the model has a certain percent of confidence, whether they see a certain type of class or not. And from there, you're basically looking at the labels as well. Initially, we actually have multiple labels from like assigns to different types of handicap spots, which we'll talk about later. But it doesn't really work after a certain scale because images vary in different data quality. But then once we get the predictions, we're able to feed that out through a simple Flask render template. And in this, what you're basically doing is that you're able to essentially just pass in different variables. In our case, we're passing in our results, and then we just run the template. And the benefit of this as well is that because you can run it on individual images, you can run a YOLO V5 model on individual frames of video as well, of any case, and any quality as well. And Arya can talk more about how we implemented that for video.
Okay, so since YOLO V5 is able to take in like images and videos, we got a video from YouTube and we just put it in a training code using our trained data set. And how it works, it just takes each frame of the video and treats it as its own image, and it like detects everything in that frame, and it just goes through every single frame. At the end, it just stitches together and like makes it one video. As you can see, like on the screen. Oh, hello. Can you replay that, Alex? Kind of stuck. Yeah, on the screen, you can see like it detects some of the cars in the back and detects some of the spaces in the front. But when there are no cars in the back, it can't really see the lines that well. So our model can't detect like all open parking spaces. And on the left side, it's confusing the brick wall for open parking spaces, which isn't the best, but yeah. And Alex will show you how it detects images now.
All right, so if you want to upload your own photo, you can just click browse, or you can drag a file in here. I'll just drag a file in here. So it brings you to these prediction results page, and you can see my results for this. It shows the image with all of the confidence levels and annotations added. You can see all these parking spots. And it shows that it was found occupied and open, since it detected an open one over here and an open one over here, and it has the large number of confidence values. So you can just click try again, and then I'm going to drag in a bad image. This one, the AI didn't do that well on, because there are a bunch of spots over here that it didn't detect, and this handicapped spot it did not detect. As Prisha and Dev said, we did used to have restricted parking, which this would be under, but we didn't have that much data for these, so it did not end up detecting this. So now I can try again with an example of a full parking lot that it actually does pretty well. And it's actually very hard to see, but it gets a lot of annotations over here. I guess thanks for watching. I hope you liked our project.